Our next probability topic is looking at dependent and independent probability. We are now moving beyond a simple probability where you are looking at only one event and what the chances of it occurring, or the situations that involve n-choose-r and NP-r, where you're looking at the probability of choosing 2 or 3 items at once. So before we get into the complexities of independent and dependent probabilities, quick review: what is an event? When we're talking about probability of an event, it is just the probability that event A occurs. And so it's absolutely anything that can be calculated. The key here is that it can't be things like a subjective probability or something that's vague. It has to be actually calculable using the probability of event A occurring divided by the probability of the sample set, all different events that can happen. What's a little different now, though, is that we're looking at this idea of compound events. And so these are more than one event occurring at a time. And the key here is that it's not just limited to 2 events, it's 2 or more separate events that are occurring. But this can be as simple as flipping a coin multiple times. It can be multiple rolls of a die, taking multiple cards out of a deck of cards. And so we can also look at things like the probability of passing all 4 of your exams. It might be a little harder, but what we would do is look at the different probabilities for each individual course and then multiplying them all together to look at that. Where we tend to get into the more typical examples would be something like a sum of 12 twice in a row. And that's really the new component here. We know that the probability of rolling a sum of 12 when you're using 2 dice is 1/36. And now we're going to have that first event occurring multiplying by the second event occurring. And we'll look in this lesson as to why we're using the multiplication part and how that ties into tree diagrams. But kind of your most classic type of question would be something where you are drawing a 4. And so that would go and give you a probability. If you're drawing a single 4 from a deck of cards, you would have a probability of getting that 4 would be 4 different cards that are all the number 4 divided by the sample size of 52. And we also have the probability of a jack, which has that exact same probability because there's 4 jacks. But now we need to kind of look at the situation of, is this independent or dependent? Is there a chance that the probability of drawing that jack is going to be altered by drawing the 4? And it gets into these situations of, where does order matter? Because if I'm taking one card and looking at it and withdrawing another card, the probability is different because I no longer have 52 as my sample size. But what if I go and put that card back into the deck and reshuffle it and draw it again? Then I do have it. So those are the kind of situations that we're going to look at in the next parts here as to when an event is independent or when the second probability is dependent on the first probability. So what are we dealing with here? Compound events are considered independent if the one event has absolutely no impact on the other. And there's many examples that we could look at here. Lots of the different kind of gaming things like spinners, like flipping a coin, rolling a die, are all ones that are designed because they have the same probabilities each time. There is that nature of it being independent. And so we'll look at kind of a classic example here where you have 2 totally unrelated things: flipping a tail if you're flipping a coin, and rolling a 3. And in that situation, when we're looking at that probability, we're going to get a probability for the tail flip is 1/2. Probability of rolling a 3 is 1/6. And then I'm going to come back to whether we're adding or multiplying this. The key is that we're using that word and so that leads us to multiplying, but let's go and take a quick look as to why that's actually the case. If I draw this out in a tree diagram, my first option was to look at heads or tails. And then from there, I have 6 different rolls on a single die that are possible. And so if I was to trace the path here, down here, I'm going to have the 3, and I'm just going to go and trace this. So if I'm looking at my tree diagram, I get a tail, and then I go down this third line here to go and get a 3. There is one option that occurs in, but I have 12 different paths. There's 12 different branches that are of the tree diagram. And so that leads me to the situation where I have a 1 in 12 chance of flipping a tail and then rolling a 3. These are completely independent. The probability of the 3 has absolutely is not impacted by whatever coin flip I had first. So we simply do this as 2 different questions and multiply them. This really isn't that different than other probability questions we've done. We've done lots of the single events, and we've done some ones where you had more than one thing that was occurring. You just treat them as individual questions and then go and multiply them together. So what gets a little bit trickier is the dependent probability. And dependent probability is always linked to the second event. So it's where we say the probability of event B is a direct result of the probability of event A. Or in other words, whatever happens the first time is going to change the probability the second time. And that's why it also gets this name of conditional probability. Okay, so what are the kinds of examples for this? Anything that's not independent. So a situation where you're having a card game, but then you pull that second card, the third card, the fourth card, and every card is dependent on what happened with the previous cards. So for example, if you're playing a game like 21 or blackjack, and you're trying to get to that goal of 21, and you've already had a 10 as one of your first cards, and then a 10 as your second card, you're already at 20. And you know that probability of an ace coming up, there's only 4 aces, but there's 2 cards that are already gone. So now I'm in that 4/50 probability of getting an ace, which is an incredibly low probability. So you would probably just hold at the 20 that you currently had. Simpler examples, you have a pencil case. There's a bunch of items that are in it, pens, pencils, markers. It's a simple probability question to remove one item, but as soon as you are removing one item at a time with multiple items, you're now in a dependent probability situation because the chance of that second pen or third pen or fourth pen is impacted by whether you pulled a pen the first time or if you pulled a pencil the first time. So those are all the different kind of situations we'll get into. Let's actually look at the math of it, and then that will help you understand when you're in one of these independent or dependent situations. So if you have a 4-color spinner and a standard die, what is the probability of spinning blue and rolling a 4 in a single trial? So first of all, quick little check here that I'm going to do on every question we do today is this an independent or a dependent situation? And this is absolutely independent because there's no way that the roll of the die is going to be impacted by that spin that I did. So what's our approach? As you can see here, 2 different probability questions. So the probability of getting a blue on the first spin is 1/4. The probability of rolling a 4, there's one way to get a 4 out of the 6 different options. Again, because of that tree diagram, we go and multiply, and then that's going to give me a probability of 1/24, which you have the option of converting to a percent, but standard probability, we tend to lean more towards the tradition of fractions. Why is that the case? Because your sample size is equal to 24. And that comes from the 6 times 4, or if we were to draw out the tree diagram, we would see that. And there's only one way that you could get a blue and then roll a 4. And this leads to our formal formula, which you might recognize from Venn diagrams. This would be the Venn diagram where you had 2 separate circles or disjoint sets. But here we're dealing with a simple probability that the probability of event A and event B occurring has to do with the probability of A happening first, and then the probability of B, with absolutely no dependence, no condition based on the probability here. And that multiplication sign is linked to the word and, because we need both of these 2 different things to happen. Okay, moving on to the next section here. So why is this a dependent event? The question is, you have 4 black and 4 red marbles in a bag. Often with these questions, it's nice to draw it out a little bit just so you can see what happens when you pick one of the marbles. What is the probability of drawing 2 red marbles if you do not replace the first one drawn? This right here, it's the not replacing is what goes and links this to a dependent events. If we had replaced it, the probabilities don't change each time. But because you're taking a marble out, my original sample size, which is at 8, is going to change as I go and take out some of the marbles. Okay, so how do we go and write this one out? Really what we're looking at here is this is a probability of having 1 red marble, then a second red marble. And I'm purposely writing it that way because it's what the question says. You draw out the 2 red marbles, but if you're not replacing it, the order matters. You're taking out that 1 red and then a second red marble. As a bit of a sidestep, previously we looked at questions that involved N choose R. And I want to be really clear here why this is not an N choose R situation. Why can I not just say there's 8 marbles and I'm choosing 2 of them? The reason is because you're not reaching into that bag of marbles and grabbing 2 at random and looking at them together. There's this idea of you look at one, you don't replace it, and then you look at the other. And that does result in a difference here. Okay, so how do I actually do the probability? Well, how many red marbles are there to start? There are 4 over 8 marbles. But now that I have taken one of the red ones out, I no longer have 8 marbles. So this is where it's nice to go over to that diagram and say my sample size has now changed. I no longer have the 8 options that are there. One of them is already gone. So for the next probability, I'm going to multiply because again, it's an and situation. I need 1 red marble and then a second red marble, but there are only 3 red marbles that are left of my 7 in total. And so this is kind of how we break down our options. Do the math here of multiplying the numerator for 12 and the denominator for 56, and then we'll reduce it down to 3 over 14. So that's the probability of getting 2 red marbles with one after the other without it being replaced. If this had been replaced, if you looked at a marble, recorded it as red, threw it back into the bag, it would be independent events. And you would just take 4 over 8 times 4 over 8 because the probability would not have changed. Okay, that's the main question, but let me just kind of go one step further here where we've now removed that red marble and our sample size is down to 6. What if the question was on the third marble, what's the probability of it being black? And so the black marble now, there's still 4 black marbles, but my sample size is at 6. So for that one event, I would have a probability of 2/3. However, and then 1 black marble gone. However, that 2/3 is just the probability of that black marble on the 3rd time. If I wanted to know the probability of 1 red, then a second red, then a black marble, I would have to go and take my original answer here and then multiply it by 4 over 6 or by 2 over 3 to see the combination of those probabilities. And that's what leads to our formula here. For probability of A and B, if they are dependent, the first event is identical. It's still just that single probability of A, but now we get into this unusual looking part where it's the probability of event B based on what happened in A. The symbols here aren't really that important. It's really just the probability of both A and B occurring is the probability of A times the probability of B, given that A has already occurred. A lot of students don't focus on this formula at all. They just take the common sense approach of every single time I'm multiplying by the new event, I have to change the numerator or the denominator based on what occurred. So that is dependent events. Okay, now let's just look at 3 quick questions that will kind of help us with these situations. And every time we're going to have to determine if it's an independent or a dependent situation. So for this first one, finding the probability of getting a 4 twice in a row with a single die. That is our classic independent situation because there's no natural link between them. The first probability does not impact the other. We've already done a question like this, so I'll do this question quickly here. 4 twice in a row will be a 1/6 probability of the first time. But then when you roll the die the next time, it's not like that 4 has disappeared. It's still a 1/6 chance of that happening, giving us a probability of 1/36 for both times in a row. For the next situation, we're going to look at taking cards out of a deck, but have one significant difference between them, and that's whether that card is replaced or whether that card is not replaced. And when we think of our independent or dependent, if it is replaced, that means that we have an independent probability. There is still 52 cards that are in the deck. But if it is not replaced is what links to the dependent probability, because there's going to be less cards as we go along. So I'm going to do both of these questions at the same time so that you can see the subtle difference between the independent and the dependent probability. So the card being replaced, reminder, is the independent situation. The card not being replaced is the dependent situation. And then we'll work through the probabilities. I'm going to focus on all the parts that are the same. The probability of the jack is getting the jack is identical. There's 4 jacks that are there. I'm going to leave everything over. I'm not going to reduce fractions right away so that we can see what's occurring with the pattern here. So 4/52 is the probability of getting a jack regardless of what's happening next. For both of them, we have that word and, so this is a probability that's going to build. It's not a separate thing. It's not an or situation. So I need to multiply. Now, what's the probability of getting a queen? If I replace the card, and all that means is you've shuffled a deck of cards, you pull one out, and it's a jack. You look at it, you record that as 4/52, put the card back into the deck of cards, shuffle it again, and pull out a card, and you wonder if it's a queen. The probability of it being a queen is 4/52. And that's because there's 4 queens and there's still 52 cards in the deck. But if I do not replace it, I no longer have the 52 cards that are there. And so the most significant difference that we have is that my probability is now out of 51. But there are 4 queens. I removed a jack, not a queen. So there's still 4 queens, but there are 51 cards that are left. And from here, we multiply and reduce the fraction. So this is going to equal to 4 times 4 is, of course, 16. 52 times 52 is 2,704. You can use technology for this, but it will go and reduce down to a fraction of 1/169. Whereas this one here goes and reduces to a fraction of 4/663. Use your fraction rules if you want, or just go straight to technology and get the reduced fraction here. This is a situation where it might be worth your time to go and convert it to percents, just so that you can see the direct comparison. But that's the main difference between calculating independent and dependent events. It is as subtle in this case as just the denominator of the second probability changing. If I had done a slightly different question of a probability of a jack and then a second jack, I would have had 4/52 times 3/51. And that's really the approach you have to take here. If it's a situation where the second probability is impacted by the first, take that pause and figure out how the fraction has changed.